Hi, my name is Amir. I'm going to fail a lot of you in this course. Welcome to Algorithms and Data Structures. This is my name, Amir Goharshady. You can just call me Amir. And whenever you have any questions, you can send me an email. You will get an answer in 7 to 10 days, usually. I'm delayed on checking my emails. Okay, so what we will learn in this course basically has several different parts. This lecture is its own part. We're going to talk about amortized runtime analysis. Then we're going to see a bunch of data structures that mostly use amortized runtime analysis. Then we're going to talk about network flows, linear programming, and then towards the end of the course, we're going to do some complexity theory, basically talking about the hardness of problems and what problems cannot be solved probably in polynomial time, and also techniques to handle these kinds of problems. So what happens if you don't have a polynomial time solution for a problem? Okay, so the course material, all of the lectures will be recorded. I assume you're all at least second-year students, so you know how to access them. I use this IPython notebooks. All of them will be released on Moodle, and they're pretty self-contained, so you can just read the slides. You will have 7 problem sheets. The first one will be released today. And of course, there are tutorials provided by the colleges. I also recommend you to read the book CLRS, this Introduction to Algorithms by these 4 people, CLRS. And also last year's slides. These are going to match this year's course pretty perfectly, but if you want imperfect matches, but probably better lectures, here are some links. I'm shamelessly plugging in my own previous courses as well. Some advice. So do more exercises than the problem sheets. The problem sheets are the bare minimum. The exams are going to be much harder than the problem sheets. Solve problems from the book or from these courses. Another point is that technically this course is 100% theoretical. So technically, you just need to learn algorithms, and you just need to be able to design algorithms to solve particular theoretical problems in the exam. But in practice, if you don't code them, you're not really going to learn them. So code all of the algorithms that you learn here, experiment with them, see what goes wrong. And actually, you will see that the slides contain implementations in Python. And this is mostly just to help you visualize the data structure. So the implementations I'm giving you in Python are horrible implementations. It's just trying to keep things as close to pseudocode as possible. Okay? And of course, each week I will also give you some coding problems. This is again not officially part of the course. You don't have to do them, but you skip them at your own peril. And yeah, you will not be examined on your coding ability. You will only be examined on writing pseudocodes by hand. Okay, let's start. So this is lecture 1, amortized analysis. I want to start with a very simple example. So consider a binary counter, and let's say that it has k bits of memory. And it starts with 0 and supports only one operation. So I can just increase the number in the counter by 1. I can increment it. And it can, since it has k bits of memory, it can count up to 2 to the power of k minus 1, and then it wraps around and goes back to 0. Okay? So it would be something like this. I have k bits of memory. I'm starting with all bits being 0. And each time I'm just doing an increment. And basically the way you do increment in binary is that you start at the least significant bit. And as long as you're seeing a 1, you replace it with a 0, right? And then you put a 1 at the first place where you saw a 0. That's increment. Okay? So let me show you an example. So I start with all zeros. I have to reverse it when I print it so that it looks natural. And if I increment and print it, it will give me 1. Then I can increment it again, 2. What is this? 3, 4, 5, 6, and so on. This is very annoying. And yeah, generally, if I do it many times, I will get something like this. So I start from 1 in binary, I go to 2, 3, so on, until I get to 7, and then I wrap around back to 0. Now, of course, this is the special case where I have only 3 bits. I can have any number of bits. So I'm thinking about k bits. So here's the question. How much time does it cost to run one call to this function increment? Well, a very easy way of looking at it is that I just want to consider the cost of changing bits. So I'm talking about time here, but let's just say my cost is the number of bits that I'm changing, because everything else is going to be proportional to it, and I'm going to do asymptotic analysis. So what is my worst case scenario? My worst case scenario is that I might have to change every bit. And that actually happens when I go from all ones to all zeros. Right. So the worst case execution time of one call to the function increment is going to be O of k, where k is the number of bits. Okay. Now, but what if I change the question a little bit? Suppose that instead of just running this function once, I want to run it n times, and let's say that n is a huge number. Then how much time does it cost to run increment n times? Well, the trivial answer is just take the time for running it once and multiply that by n, and you will get O of n times k. Okay. This is actually a correct analysis. It's just kind of naive. It's loose. So let's do some basic experiments here. I'm going to keep track of my cost. So I added a variable r, which basically keeps track of how many bits have changed. And let's just do this. I try it with different values of k and n. So let's say k is 3, I have 3 bits, and I'm doing increment 10 times. I want to see what is my total cost. In this case, it's 17. Now let's increase n. So let's say, I hate Windows. Okay. So if I do to 100, my cost almost multiplied by 10 as well. If I go to 1000, again, the same thing is happening. So it seems like my cost is linear in n. But is it also linear in k, as we would expect? So suppose that I start with 20 bits, and I run it. And this is my cost. And now let's say I have 200 bits, and the cost is the same. It's not really changing, right? And I mean, you can experiment with this and try different values of n and k. The important thing is that although we found this bound, n times k, in practice it seems like it doesn't really depend that much on k. It seems like it's just linear in n. Now, let's go back to theory and let's see how we can prove such a thing. So here's how I can look at the same problem. I can say I have this array A, and this is my array of bits, and I can look at each one of my bits and see how often that particular bit is going to change. Right? So if I look at A0, it's going to change in every operation. Every time I call increment, my 0th bit is going to change. Right? Because that's basically the parity of my number, whether it's odd or even. If I look at A1, it's going to change every 2 increments. And so on. A2 changes every 4 increments. AI in general changes after every 2 to the power of I calls to increment. So if I sum all of these things up, I know that my total runtime is going to be at most this. Sum of I from 0 to k minus 1. And then this is, floor of n over 2 to the power of I, but I can just over-approximate it and ignore the floor. Right? But then this is just 2n. So my total time is at most, or my total cost is at most 2n, which is in O of n, which is exactly what we expected based on that small experiment that we did. Right? Now, here's the thing. In this case, doing worst case analysis on each operation actually gives us a very bad bound when we're running our operations many times. So instead, we try to take an average. We say, look, if I do n operations, it's going to cost O of n. So it seems that each increment operation on average takes O of 1 time. Right? So this is what we call an amortized runtime. So I would say that the amortized runtime of increment is constant. It's O of 1. Okay. Let's formalize this a little bit. So let's say that I'm doing n operations, and the ith operation has a cost. I'm going to call that Ci. So my total cost is going to be just the sum of the costs for all the operations. Now the crude way that we just saw at first is that I can just take the maximum cost over all of my operations, and I can say the total cost is bounded by the number of operations times this maximum cost, right? But we don't want to do this. Instead, we want to find some other value, and we want to say this. I say that the sequence C1 to Cn has amortized cost big C if basically the rolling average cost never exceeds big C. So if C1 is less than C, C1 plus C2 is at most 2C, and so on. So in general, if I look at my first I operations, their cost should be at most I times C. Okay? This is just saying the same thing in a slightly different formulation. I just say that C bar I is the rolling average until the ith operation, and then I say my amortized cost is the maximum of these rolling averages. Okay. Now, an interesting thing that you can think about, but I'm not going to go into, is how you would extend this if you have several types of operations and you want to assign different amortized costs to each of them. So you will have to generalize this a little bit. Okay. But today we're going to see 3 techniques for amortized cost analysis. These are called the aggregate, accounting, and potential function methods. I never understood why people say these are 3 different methods. They're just using the definition. All of them are the same. Okay, and you'll see. I'm just going to present it the way that it's always presented. I always thought it's a bit dumb that they call it 3 different methods. Okay. So, the first method, I don't know, again, this is not a method, this is just a definition, is that I basically want to aggregate all the costs. So I try to find some asymptotic upper bound T such that for every n and every possible sequence of n operations, the cost of these n operations is at most O of T, right? And then I would just say, well, if I have n operations and they cost O of T overall, then the amortized cost per operation is just T divided by n, right? This is exactly the analysis that we saw for the counter. This is using the aggregate method. So let me give you another example. So consider a stack. So a stack is a data structure in which you can just add more and more items, but each time that you want to take an item out, you take the last item that you pushed. Okay? So I have 2 operations. I have push x, which adds x to the top of my stack. And I'm literally thinking of a stack of dishes here. And then I have pop, which just removes the top item from the stack. Okay? And I'm assuming that each operation has a unit cost. Oh, by the way, we generally use amortized analysis to do runtime analysis for our algorithms, but it can be applied to any kind of cost analysis, right? So the cost is just something I'm defining. So I don't really care how this data structure is actually implemented. I'm just assigning a unit cost to push and pop. Okay? Great. So I can have something like this. This is just an implementation. And I can do some experiments. So I can push 1, push 2, so on, and then I can do a bunch of pops, and then I can do more pushes. Okay. There's nothing interesting here because we have 2 operations and we are saying that by definition they have unit cost. What makes it interesting is if I had a new operation and I'm going to call this one multi-pop. And basically the idea is that it takes some parameter k and it pops the top k elements from my stack. So it's just going to call pop k times, assuming that there are k elements in the stack. Okay? So here's how I'm doing it. I'm just basically calling pop k times. I'm just checking that I don't call it if my stack is empty. Okay. And again, remember that the only cost that I'm paying is just for push and for pop. Okay. So if my stack is this, 1, 5, 6, 7, 8, 9, and if I multi-pop 3, I will just get 1, 5, 6 because it removes the last 3 elements. By the way, in my codes, I have a lot of printing. I'm not accounting for the time it takes to print stuff because I just want to show you how it works. But of course, printing is not free. So in practice, if you print something, you're paying for it in runtime. Okay. So here's the question. What is the amortized cost if I consider all three operations, push, pop, and multi-pop? You know? And the answer here is 0.1 for all three of them. But just before going into this, if I wanted to do a worst case analysis, push would take O1, pop would take O1, but I would expect that multi-pop takes O of k, where k is that parameter, right? But if I'm doing amortized analysis, I can claim that all of them take constant time. It's O1 for all three of them. Why is this the case? Well, I can again analyze it using the aggregate method. And the basic idea is that I'm never going to be able to pop more than I've pushed, right? So whatever my runtime or total cost is, it's going to be some constant times the number of pushes. It doesn't matter what else I'm doing here, okay? So to be a little bit more specific, all costs are incurred by either push or pop, and this can be a pop that is called by a multi-pop. And pop cannot be called more times than push. Now, if I have a sequence of n operations, at most n of them are pushes, right? So my total time or total cost is 2 times n, and my amortized cost is just going to be 2, which is a constant. Okay. Great. Any questions so far? Pretty trivial, right? I promise you the next sessions will not be like this. Okay. So here's the accounting method. And this is honestly, again, just the same method. I keep saying this. It's just the same method. We just visualize it a little bit differently in our mind. And this is the visualization that we have. So the intuition is that I'm going to have a bank account, and I'm going to assign a charge. I'm going to call that xi to every operation in the sequence. Now, my bank account is initially empty, and every time that you want to do some operation, the ith operation, I charge you xi. So you have to pay me some random charge that I have chosen, which is xi. And you pay me this amount in cash. Now, there are two cases. Either the amount that you paid me is more than the cost of the current operation, in which case I pay for the current operation using the amount you paid me, and I put the rest of it into the account. I just deposited it. And there's also the equal case, of course. Or if what you have paid me is less than the cost, then I have to withdraw the balance from the account to pay for this operation. So I have to withdraw ci minus xi from the account. Now, I can't have overdrafts, so the account balance always has to be positive or non-negative. Okay. So if your account balance never gets negative, then you can be sure that the sum of the costs is less than or equal to the sum of the charges, right? And you can also be sure that this holds for any prefix of the operations, okay? So you can say that the amortized cost is at most the maximum of the individual charges. And this is just a rolling average thing. So the idea is that you sometimes prepay for your future operations. So if you have a lot of operations and you think that some of them are going to be really expensive, but they're kind of rare. So imagine, for example, multi-pop. So I'm thinking that I'm going to do many more pushes and pops than just multi-pops, right? So every time I do a push or pop, I save some money in my bank account, and then when I have to do a multi-pop, which is an expensive operation, I'm going to use that money to pay for it. That's basically all of it. Okay, it's really like second grade math. So here's how we would analyze the binary counter if we want to do the same thing. So I can just look at the bit flips whenever I'm changing a bit from 0 to 1 or 1 to 0. We said that the cost is just 1, right? But I can assign a different charge. So I can say that whenever I flip a bit from 0 to 1, instead of charging £1, I'm going to charge you £2 for it. Now, the intuition here is that £1 is the actual cost of this operation, and the other one is just going to be saved in my account to later pay for flipping this bit that is now 1 back to 0. Right? And whenever I want to flip a bit from 1 to 0, I charge nothing. I just have the money in my account. I just use that to change this and pay for the cost. Okay. So, yeah, this shows that the maximum of all the xi's is 2. So the amortized cost is 2, which is O of 1. Okay. Yeah, this is basically just adding comments here. I don't think I have to do anything. Okay. Yeah, we can basically do the same analysis on the code. So if you look at the code, actually, here when I'm setting a bit to 0, I'm just withdrawing from the bank account. And here when I'm setting the bit to 1, I'm charging £2. So every time that I'm calling increment, of course, I'm going to reach this line of code at most once. So I'm going to charge at most £2. Sometimes the charge is 0. When is the charge 0? Yes. Yes, exactly. So when it's all ones and I'm doing a single increment and it's going to all zeros, I'm just using my bank balance to pay for everything. Right. Now, the really important thing, and I mean, the only thing that people can screw up when they're doing this kind of analysis is that you have to make sure your balance never falls below 0. So that's usually called the accounting invariant. You have to always prove that. If your balance goes below 0, the analysis doesn't work, of course. Okay. So let's do the same thing with our example of stack with a multipop. So again, every time that I'm doing a push, I'm going to charge £2. And I'm going to use £1 for the actual cost of the push. I'm going to put the other pound right next to that item so that I can pay for it when I want to pop it. And every time that I'm doing pop, no matter if it's just a normal pop or it was a multi-pop that called this pop, I'm just going to use the £1 that I have next to this item to pay for its removal. So every operation, again, has a charge of at most £2. And again, importantly, my balance never falls below 0, so the amortized cost is constant. It's O of 1. Okay. Now, we're going to have another one, which is the potential function method. Now, this one is also kind of like the same again. I think it's a special case of the accounting method. So the idea is that I'm going to assign some potential energy to my data structure. Okay. I mean, we're pretending like we understand physics, but we're computer scientists. We don't. It's just a function. So I'm going to assign a potential energy to my data structure, and this is basically my bank balance. Okay. So again, I don't know why this is considered a different method. I assign some potential energy. So let's say that Q is the set of all possible states that my data structure can be in. And I mean, Q is, of course, an infinite set. And I'm going to assign a function phi, which basically takes every state and gives me a potential. Potential cannot be negative. Right. And I'm going to do a very slight abuse of notation. Now mathematicians are going to hate me as well. And I'm going to write phi I for the potential at the state right after the ith operation. So if that state is qi, I don't want to write phi of qi. I want to just write phi I. Okay? So, again, I want to assign a charge for every operation. And whenever an operation takes place, of course, there is a real cost that I have to pay. But then I have to also pay for the change in the potential energy. I can't not laugh at this, it's just ridiculous. I have to also pay for the change in potential energy in my data structure. So the charge that I'm assigning for the ith operation is going to be Ci, the actual cost of this operation, plus the potential after the operation minus the potential before the operation. Okay? Now, it's very easy to see again that this potential thing is just your bank balance, and the sum of the xi's is going to be the potential after all operations minus the potential at the beginning before any of the operations plus the sum of the CI's. Right. So all I'm saying here is that the sum of the charges is going to be the change in your bank account balance plus the sum of the actual costs that you paid. Okay. Now, normally, we choose our function phi so that our initial value phi 0 happens to be 0. Because if I do that, then I can just get rid of this phi 0 here, and then the phi n is positive, so I can just say the sum of ci's is at most the sum of xi's. Oh, another thing that you have to get used to in this course, sometimes I say positive, I just mean non-negative. Okay, so those special cases you have to figure it yourself. So phi n is non-negative actually here, and phi 0 is 0, so I can say that the sum of ci's is at most the sum of xi's. And then, just like before, I can say that the amortized cost is at most the maximum of all the charges, maximum of all the xi's. Okay. So the intuition is again kind of obvious. We pay for our expensive operations by reducing the potential energy saved in our data structure. Okay, and then finding the right potential function is an art. There is no standard way of finding the function. And you will actually see some data structures in this course which are super simple, and then finding the function is the hard part. And I just have one question for you. I said that we usually choose our functions such that the initial potential is 0, but does that matter? So does it matter if phi 0 is 0? It doesn't. You can basically have any other constant, because at the end of the day, you're taking the average, you're dividing by n if you have n operations. So if it's a constant, it's going to give you the same result. There is only a corner case where it would matter, and that's when you're assigning an amortized cost of 0 to something, but don't do that. Okay. So just don't go below constant. Okay, everything is O1 and not less than that. Okay. So let's do this potential function method. And let's first do it on our example of the binary counter. So I say that the potential of my array A, which was my counter, is just the number of bits that are set to 1. Okay. So why does this potential function work? Someone just, it's pretty trivial, right? So what are the things that I have to check about this potential function? I have to check that it's non-negative. But I mean, of course it's non-negative. It's the size of a set, right? And what is the charge that I'm actually paying? What is the xi that I'm going to pay? Yeah, it's at most 2. Okay, so why is that the case? So my charge is just the actual cost and also the change in the potential. Okay, but when I'm setting a lot of bits from 1 to 0, when I'm reducing this potential, it's also paying for it, right? So reducing potential can be used for paying for operations. So the only case that I have to really pay by charging you is the case where I have a 0 and I'm setting that to 1. But that happens only once whenever I'm calling increments, right? Great. Again, the only thing you have to check really is that the potential function doesn't go below 0 and that you can find a good bound for the xi's, and the bound here is constant. What about the case where we had a stack with multipop? Well, if I have a stack S, I can say that its potential is just the number of elements in S. Okay. And again, you see here that the idea is pretty much the same as my bank account balance. It's effectively doing the same thing. Now, why does this potential function work? Well, again, I have to just check that it's always non-negative. It's the size of the set, so it's non-negative. And what is the actual charge xi? So I can again look at push and pop separately, right? what happens when I'm pushing? When I'm pushing, my potential is going up. So I have to pay for that. But it goes up by only 1, right? And there is the cost of push itself, which is also 1. So when I'm pushing, my charge xi is just 2. When I'm popping, my potential is going down by 1. But then, if my potential is going down, I can just use that to pay for the operation. And when I'm multi-popping, it's just the same thing k times. The potential is going down by a value k, and I can use that to pay for everything. So again, this xi is bounded by at most 2, which is a constant. Okay. Let's just see another example. And this example is called a dynamic array or a dynamic table, or for those of you who program in C++, by the way, I love you if you program in C++, it's called vector there. So the idea is very simple. We have some array A, and we have only one operation, insert. And it just adds some number or some item x to the end of the array. Okay. Now, yeah, again, in C++, this is pushback. And the problem is that we don't know how much memory we need. So we don't know how many times this function insert is going to be called. That means that I have no way of knowing how much memory I have to allocate before the program is actually executed. Right? So if I run out of memory at some point, so let's say I have an array of size 10, and I have already inserted 10 elements, and now I'm inserting an 11th element. The only solution I have is to allocate a new bigger array and then copy everything to this new array, right? And that's going to be expensive because, of course, copying each item is going to have a cost of 1. So to be more precise, our cost is just the number of copy operations. So it can be either I have an array which is not full and I'm just copying x to some element in this array, or it can be that my array is full, so I'm allocating some bigger array and then copying all of these elements. But I'm paying a cost of 1 for each copy. Okay? And the question is, can we do this in O1 amortized time? And the idea is very simple. The idea is, well, what can I really choose in this data structure? I really don't have much of a choice on when I'm doing the extensions, because I would only do the extensions if my array is full. The only real choice I have is how much I extend my array. And the idea is kind of similar to binary search. So I say that every time the array is full and I'm doing a new insertion, let's double the size of the array. Okay? So this is what I'm going to do. I have my array. I use 0 to show some element of the array which is not used. It has a size, which is the amount of memory that is allocated to it. And I also use this num to know the number of items that are currently in the array. So when I insert into it, I just check. If my array is not full, I just copy this x into the array, and it has a cost of 1. Otherwise, I have to create a new array of twice the size of the original array. And then I have to copy every element of the original array into this, and each copy has a cost of 1. And again, as usual, I'm printing my arrays, and I'm not considering the cost of printing. So here's a simple example. You can see that I start with an array of size 1. When I want to insert the second element, I have to double the size. My print is called twice for some reason, sorry. And then when I want to enter the third element, again, I have to double the size to 4. Then I insert the fourth element, and here I already had room for it, so there's no problem. But when I want to add the fifth element, I have to again double the size to 8, and so on, and then double the size to 16. Okay. So we want to analyze the amortized runtime. Maybe I shouldn't have come to this. So forget this slide for a second. What do you think the amortized runtime is? It's O1. Yes. Okay. Great. So let's formalize this. So I can do the aggregate method, which basically says I have a sequence of n operations. what is the maximum cost that I can possibly have over a sequence of n operations? What is the maximum total cost? And basically, I'm going to do a casework. Either I'm extending or expanding my array, or I'm not, right? So let's do these two cases. In which cases am I going to extend my array? So I have, let's say I'm at the ith operation. When will I extend my array? If my array size is already a power of 2, and it's already filled up, right? So if I minus 1 is a power of 2, then I have to extend my array, and then the cost in this case is I, because I have to copy all the I minus 1 elements that were already there, but I also have to copy the new element x. So it's a cost of I. Otherwise, if my array already has some empty space in it, I'm just copying x into my array, that's a cost of 1, right? So if I'm doing n operations, I can find my total cost. I can say, well, I have at most n of these cases, and let's just find the costs in these cases, which is just the sum, and that's in O of n. Okay, so basically my cost is n plus the sum of all the powers of 2 that are smaller than n. So again, because this overall cost is O of n, the amortized cost per operation is by definition O of 1. Okay. But now let's do this with the potential function method. So I want to assign some potential to every state of my array. And basically I care about two things. I care about the size of my array and the number of elements that I have there. And remember, the main intuition was that whenever I'm doing something really expensive, I want my potential to go down. I want my potential to basically pay for it, right? So let's do something like this. Let's say that my potential function phi is 2 times num, which is the number of elements, minus size, which is like the amount of memory I have. Okay. Now we can just do the same casework as before. And just remember that the charge for the ith operation is the actual cost of this operation plus the change in the potential, right? So if I don't extend my array, what happens to this potential function? Well, the size remains the same because I'm not extending, but this num is going up by 2. So phi minus 1 is just 2. And the cost is actually just 1. So I have to pay a charge of 3 in this case, 1 plus 2. But what happens if I have to extend my array? Well, then in that case, my size is doubling. So let's say that before I did the expansion, my size and the number of elements were, of course, the same. I'm going to just call that m. So my cost is going to be m plus 1, because I have to copy all the elements, including this new element that I'm just inserting. Right? What is my potential before the operation? I just plug it here. It's 2 times m minus m. Again, num and size are both m, so it's just m. And what is my potential after the operation? So now the number of elements has increased by 1, but the size has doubled. So it's 2 times m plus 1 minus 2 times m, which is just 2. And then, again, you just plug it in, and the charge that you have to pay is the cost plus the change in the potential, but the change in the potential was negative, so the change in the potential paid for most of your cost. The only thing that you have to pay here is actually just 3. So in any case, my xi is constant, it's in O of 1, so my amortized runtime is in O of 1. Okay. So let's make it a little bit more interesting. Let's say that I have the same kind of array, but now I'm adding a pop operation. And this pop operation just removes the last element of A. Now again, this is still not that interesting because I can say that each operation takes O1 amortized time. Because when I'm removing an element, that's really nothing. I'm just putting a 0 in place of it, right? So as long as I'm not changing my array, I can do pop in constant time. But then the issue is that maybe I push a lot of elements and maybe I pop most of them, but I'm now wasting a lot of memory just keeping a huge array. So I'm going to make my life harder by defining a load factor. And the load factor is basically the ratio of the memory I have allocated that I'm actually using, the number of elements divided by the size. Okay. And I want to require that this load factor doesn't just become arbitrarily large. So I want to say that there is a constant and this load factor is at least, I want to say that it does not get arbitrarily small. Oh, I was thinking, okay, there's some smaller error here. Anyway, so I want to bound it by a constant. And the simple idea is to do the opposite of what we were doing before. Basically, we can say whenever my array is only half full, let's cut it in half. Okay. Now, unfortunately, this will not work. So don't look at this code too much. It doesn't matter. It's basically just doing what I told you. It's saying that when I'm doing pop, I remove one element, and the only way I'm removing that element is by just reducing the number of elements. I'm not even doing anything. And then I'm going to say that if the number of elements is less than half of the size, create a new array, copy everything over. Okay. And as usual, I have the prints there. So I also added some code that sums up the costs and give me the costs that happened in every step. So when I'm inserting 1, that has a cost of 1. When I'm inserting 2, it has a cost of 2, and so on. Okay. Now, here's the case where everything breaks. So suppose that I just keep inserting a bunch of elements in my array. And of course, when I do that, my array keeps getting bigger and bigger. Right? And let's say I get to this point where my array is kind of half full, like one element more than half full. And then I remove that one element. And the size of my array goes down. I'm shrinking my array. But that's a very expensive operation. I have to copy everything when I'm shrinking. But then I insert again. Now I have to double the size of my array again, copy everything over, and then you can guess what I'm going to do next. I'm just going to remove, add, remove, add, remove, add. And now every operation is taking omega n time, where n is the size of the array. So this is just awful. I can't have a better asymptotic, amortized asymptotic runtime here. And the issue is that we shouldn't be so eager in cutting our array in half. So the way we can fix this, and this is a very simple fix, is that we just add some slag for deletion. So I say that whenever my array is full, let's double the size of the array. Okay. But the only case where I cut my array size in half is if it's a quarter full. So if the load factor is 0.25. Okay. So the intuition is that I want to kind of keep my array close to half full at any given time. Right. So I want to keep my alpha close to 0.5. Now, I'm too lazy to analyze this. So this is going to be an exercise for you. You're going to prove that both operations have O1 amortized costs. And the thing that would be interesting is to try to do it using all three of these methods. And try not to cheat. So try to actually come up with the potential function without looking at the accounting method and so on. Because it's really easy to translate between them. But if you want to use the particular intuition of each method, it would be a little bit harder. And especially for the potential function, I can just give you a hint. So imagine a case where you have a really large array and already you have a lot of elements in it and you only have delete. Okay, that's your only operation. Try to find a potential function for that case, for the case where you have only the delete operation. And then try to combine it with the potential function for the case where we only had the insert operation. Okay? And this is actually a very common technique. So sometimes it works. I mean, it's not guaranteed to work, but in many cases it does work. That you just find different potential functions for each of your different operations, and then you try to make your overall potential function just a linear combination of them. Okay. Great. So that's one thing I want you to think about. The other thing is we have two constants here, and I just made up these constants, right? So I said double the size of the array when alpha is 1, half the size of the array when alpha is a quarter. I want you to find all the constants for which this would work. So what constants can I plug in here and here so that I still have O1 amortized cost? Yeah. Finally, some optional resources. Read the CLRS chapter on amortized analysis. This is either chapter 17 or 18, depending on which edition of the book you use. Learn about the thing that I'm using here to show you the slides, Jupyter Notebooks. There's a YouTube link there. You can just watch it. It takes 10 minutes. And register here for access to coding practices. Yes. But this is, again, I'm going to add practices every week there. It's not going to directly affect your score. So you don't have to do it. But again, you skip it at your own peril, because a lot of the ideas that you will see there are going to actually help you solve algorithmic problems in a better way. Okay, so I'm going to put these slides on Moodle, and I'll see you on Friday.